I really want to move forward to get to hacking. I'd like to actually get us hacking by 11:30, so you have an hour. So we should form. So, but give me half an hour. I'm just going to finish going through this model, and I'll show you the DICE 2013 stochastic programming model, which is just an edited version of the last model. I dropped some stuff that was irrelevant, and I basically cleaned stuff up, put the two-stage, the stochastic programming stuff in, and I put in one type. I put in uncertainty about catastrophe. So the idea would just be, as a group, to just take the model, perhaps put a different type of catastrophe in, different type of, just make a decision about something, run the model, collect the results. But I'll show you that stuff. But first, let me just finish going through this little paper. So this is ESUB. We've talked a little bit about the elephant and the rabbit. The utility function in this model is calibrated. So I take E bar as the base year energy demand, C bar is the base year consumption, non-energy demand, epsilon sub t is the energy value share. And here I'm just teaching a little bit of microeconomics. It's seemingly redundant. Mathematicians, in general, if you're a mathematician, Occam's razor tells you're better off. If you have the same function and one has more parameters than the other, you're always better off with the one with fewer parameters. With calibrated models, not true. It's one of these things where you make conscious decisions to work with a function that has more parameters because it's easier to work with. You can see what's going on. And the key idea is unit functions are your friend. A unit function is something that takes on a value of 1 when you're close to where you think you are. And that's what happens here. Notice that we're a unit function. If I have E equal E bar t and C equals C bar t, those are both 1. Then it's epsilon plus 1 minus epsilon. That's equal to 1. It gives me a value of 1 right off the bat. So it makes the process of sort of working with the CES function much easier. If you're the type that's more easily motivated by if you're more easily motivated by Excel files or pictures, then here's a picture with the same model. Again, see if this works. So there I'm changing the elasticity of substitution. So that goes from 0 to 1 to 0.5, just like in Mann's paper. And here the benchmark price of X, if I make X more expensive, and I make the scenario price more expensive, then I change the calibration point. Once I've calibrated the model, I've tied it down. So the point is I observe how much energy and non-energy gets consumed at the point. I observe that stuff is given, and I impose an elasticity, and then if I change the price of X, if I increase X, that changes where the demand response just has to do with how much does energy change as the price of energy changes. So this is all basically should be taught in third year undergraduate, but a lot of times people are not so oriented to how the world is. They're kind of in microeconomics lives its own little world, and there's not enough emphasis on how do we make that model fit what we observe, right? So this is how you make this thing fit. And everything is here. The thing that's nice about this spreadsheet is it's all completely open. You can see everything right there. That's the whole control. You can go through and see exactly how it all operates. So that gives you the whole, basically, of the story. So that's included in the distribution. So here I'm doing the calibrated CES, energy value share. So that goes just reminding you of how this works. So what are the equations in this model? So again, it's the same idea. We have this ELF, this economic loss factor, which is the non-market damages in the MERGE formulation. So this is most of this is based on the demand side of MERGE and the MERGE climate model. So it's really similar to DICE. There's not that much difference. Here we have new vintage utility, and then we have GDP. GDP is equal to, ref is equal to C plus I plus MD. This is set up because we're treating the model as though I'm making the assumption in the first year I know investment, I know everything about the first year period. So that's the reason I'm going to fix C, E, and MD in the first period will all be exogenous. And if I'm going to fix those variables, then this equation is sort of redundant. I don't need it for the first period. So if I index the equation over t plus 1, then that skips the first equation because all of those guys are fixed. So there's the Putty-Clay formulation, which is cool, where speed is fixed and exogenous. So the cool thing is Charlie's working on a version where speed is endogenous, so you can do things to make this, generalize this a little bit. There's the CO2 climate submodel. You have just boxes of CO2 moving around. Again, I'm not going to go through this, but you can see it's very similar to the way that DICE works. So here it gets down to radiative forcing, equilibrium temperatures long term, and then actual temperature is the lag process that depends on. So there's this rate of convergence to equilibrium temperature, which depends on these speeds, this lag factor. And then the market's damage is then proportional to the average temperature change divided by the reference temperature. And that's the market damage. And then the economic loss factor has got this hockey stick exponent HSX. So you can see this is all described in the various papers that Alan Mann and Rich Richards wrote over through the 90s. There's a number of different papers that describes it. So that's all fine. And here then is the equations that describe catastrophic loss. Here I have a fixed. So here I have a proportional factor that's proportional, the change in temperature is proportional to the hazard rate. And there's the evolution of the probability of not having hit a disaster, and there's the probability of disaster at the given time. And then here we have the elasticity along state S. And so this is saying, again, I'm going down this tree, and once I get after, so that's after the disaster, state S and time period T is after the disaster, then we have a catastrophic loss in that period, represents the discount, the effect in there. Otherwise, we're before the disaster, then we have the economic loss factor. So it's got market and non-market damages and catastrophe. And then we have this coefficient of relative risk aversion that describes the substitution across states. So I promised at lunch, at breakfast, there was somebody, our colleague from Kiel. No, you're from Potsdam. I forget your name. Ulrika. So Ulrika was telling me about how to manage scenarios, which is something, if you're just a beginner, it's like, what's this? How do I manage runs of GAMS runs? And I'm going to show you my latest and greatest. This is the latest and greatest. This is something I'm always messing around with. Every time I get a new machine, it has a different number of processors. How do I use my machine? Every night, if I'm working on models, every night when I go home, I feel better leaving when I know my machine is doing something that I will be interested to look at the next morning. And it's always like, how hard can I push that processor? And I burn out processors all the time. So I go through machines like every 6 months, I blow out another machine. So this just is something that just happens. But it's fun, and I'm still learning. I haven't been that successful yet at Wisconsin on learning how to use the network. We have a network with like 800 cores, and I'm a bear of very little brain. I like to use my machine, but I like to run lots of processors at once on my machine because I'm under control. So this is the way this is set up. So you say GAMS model output is equal to compare. That says generate an output file with results in compare.xls. That's basically a report for the current run. And then I have this thing called SSA setup that says generate a systematic sensitivity analysis for me with the parameter values that are specified in that program. It's a GAMS program that writes a batch file to run the model. And then it says start SSA run. So there's the thing that runs the model. And then so this program SSA setup is a twin is siblings. We have one that runs at the beginning and another called SSA pivot that runs at the end. Because what we do at the beginning is we set all the combinations of the inputs we want to run. Each combination gets a scenario number, and then at the end we want to unpack the scenarios we've been able to solve and reassociate them with the parameter with what we've run. And that way you get a pivot table with a pivot table tells you all of the inputs, and you can pivot through and see all the results that come out of the model across all those different scenarios. So it's a very nice little tool. And then you can say start pivot report.xls. Before you get too enthusiastic about what's that great TV show, Curb Your Enthusiasm? I love this. So you have to curb your enthusiasm a little bit. Yes, life is good. Under Excel, you get 1.5 million rows. The bad news is when you start going with this thing, you can hit that limit pretty quickly. So you have to be a little bit careful about how much stuff do I want to harvest out of every run and how many runs do I want to do. So there's a little bit of care is useful, but this is a good way to get lots of stuff generated. So within the SSA setup, these are the model-specific values. You specify what is the guy you want to change, and then what are the values you want to give to it. And if it's a dot in it, you have to quote these labels because otherwise it'll think that it's anyway. So this is basically just you quote all the things and you say, okay, so what's the coefficient of relative risk aversion, 0.5 or 1? What's the catastrophic cost, 0.5 or 0.9? What's my prior about the likelihood of catastrophe, optimistic or pessimistic? What's the elasticity of substitution of energy for non-energy in new vintage production, 0.25, 0.7, 0.5? What's the Petit-Clay decay rate? So you basically, and I like this with little models. With big models, this is not so useful because with big models, you can't run that many. It's more, I'd like to distinguish between piecemeal sensitivity and systematic sensitivity. Systematic is most useful for small models because you want to then quickly see what are all the assumptions and how do they come out. So that gives you the basic setup. And then if we go to the directory, so if I go, so there's catastrophe. That's the reason the file's a little bit big. I'm just showing you what you would do. So you would make a directory, you copy catastrophe.zip into the directory, and then you go in the directory, unzip, whoops, GAMS has an unzip in it. So you unzip it, and then that gives you those files. And let's first look at them. So there's the model. And I just wanted to show you in the model, again, this is, for beginners, I apologize. I'm trying to design a class to talk to different people, and some people, if you're using GAMS, now I'm talking to people who've used GAMS before, this is the technique for controlling your model. So the whole thing is once you get a model that runs, you want to know what's important, what drives what. And that's where this instrumenting the model is a good thing to do early on. And here the instrumentation consists of environment variables are the way to go for instrumenting a model because they can be controlled from outside the model. So if I declare an environment variable, I say, here I'm saying, create an environment variable called irate and give it a value of 0.05. This syntax says that is the default value for irate, and if it's not set, that means if on the invocation it's not been set, then it gets set there. And once you've got that, then if we look, search down below, oops, that one didn't get set. It should have been like that. So it should have been, so you basically have, I apologize, that one didn't get, I guess I didn't use that one, so it didn't matter, but if I look for cat cost, so cat cost gets assigned. So here you have the variable at the top. So at the top of the screen we have the variable that says, the top of the screen tells you the variable cat cost has a value of 0.9, and the bottom of the screen you see it gets assigned. And so this is just, it operates just like a string substitution. And so the beauty of this is you can have a control variable, an environment variable that's controlling the model, can set a numerical value, but it can also control structure because you can use it to what version of the model you want to include. So you can do all sorts of stuff here. You can use it for an include file. You can use it for anything in the program. So it's very powerful. So this sets this model up. And then if we go outside, I don't know how fast this machine is. I say GAMS, let's just see if it works. So there it does compile a GAMS model. So there it works through fairly fast. It does a bunch of simulations. And then that's done. So if I say then GAMS SSA setup, that just runs the program called, runs, if I look at the batch file, it generates a thing called SSA run. The default setting for me is for 4 processors. So this is just the thing that went through and generated this file and has a different version. One has different versions for each processor. So this is basically saying if it doesn't have an argument, then it goes to checking the processors and it assigns. It's going to start the runs in the first processor, sleep for a second, start the runs in the second processor. Turns out if you try to launch multiple jobs simultaneously, you run into collisions. So it's taking a little bit of time in between. I love that about computing. It reminds me of like woodworking or something. There's certain times you have to leave a little bit of time before so things don't crash, right? So it's kind of fun. So then this is going to say, and you can see the runs that this says, in scenario 1, it does GAM's model, put the output to the listing file into 1.lst, save the GDX file, and then for each of the values from the thing, it assigns a value to each of the parameters for that scenario. So it just goes through all the combinations of the inputs, generates one scenario for each combination, which can be brutal if there's lots, but you want to basically, it's not just something to do before you go to bed or before you go to leave the office in the afternoon, start it running, you can get runs back. So it's a way you can run lots of cases. And then once we've done, so let's see if this works. So if we just go here, so if I say SSA run, so the beauty of this is we get one window for each processor. And the reason that that's cool is because if suddenly you decide you have to use your machine for doing something else, then you can pop over to that window and hit Control S. And you can stop them, right? You guys weren't even born. And the Control S is a command that goes back to the PDP-11, 1974. It's the same command. Stop this process. It just stops it so then the processor doesn't move, and then it doesn't use any resources. And when you want to start it again, I think in Windows, just hit any key and it'll start up again. So then that goes. So that way you have control over your machine. And what's more, if you just want to glance at it, you can look to see, well, how's that processor doing? It tells you what percentage of the jobs it has completed at that stage. So this is a useful, and because there are comments in the SSA setup, so these routines can be used, they're general. Just edit the top. There's indications in the files of what they are, so you can use them on any sort of GAMS program. I haven't got it operating yet, but I'm working in a version where you can have an Amazon cloud account, and then you can run the thing and it'll launch onto the cloud. So I'd like to have it so I can run 3,000 at a time, right? So you can, because the cloud computing is actually very cheap. It's just a matter of figuring out how to establish the thing so you can get it set up. But it's going to be, it won't be long at all. I mean, it'll just a matter of months, I think, before it'll be possible for you to pay, 10, 15 bucks a month, and then you'll have basically unlimited compute ability, and you won't have to wait. You just hit the button, it does all 3,000 of them at once, and all comes back. So the world is changing a lot. This ability to run lots of scenarios is really, once you have a model and you have the compute power to do it, you want to use that power to figure out what's driving things and understand. And so, they're almost done. I don't want to wait too long. So that one's done. That one's done. That one's done. That one's done. And then we say, and the SSA pivot, then it zips together all the PDF files and generates them all into one big pivot data file. So you get all the results put together for the stuff you saved. And then it puts them, it takes some time for it to generate. And I'm not sure on this machine whether it generates the Excel. There's these differences in terms of how Excel operates. So that's the basic story. So and again, I apologize if you're new with GAMS, this stuff may look a little arcane, but if you're using it, this is something I think you might find useful. So finally, let's look at the dice model. Something seems to be. You know, Microsoft has like thousands of programmers. GAMS has like 6. But the GAMS guys are completely, they're solid. They produce stuff that's always works. And Microsoft is incredibly sloppy. Sometimes how stuff works is really, anyway. So this is the GAMS SP program, so the DICE SP. So I basically took the same model that you guys have set up on your machines last time, and I just edited it a bit to incorporate the uncertainty. And I also chopped the model up so it's easier to see what's going on. It gives a little bit more. There's generally this trade-off. If you're good at an editor and you can move back and forth and search, then you like to have stuff in one file because then it's easy to go just through that file. If you're getting started and you kind of wanted some guidance as to what's where, then having the separate files is useful. So here I've chopped up the DICE model into one file called sets, another file called parameters, another file called equations, another file called initialize, another file called solve. So it's just basically, those are the basic sets, the steps. What are the sets, including what's the stochastic structure? What are the parameters we need, declare the parameters, get the values. What are the equations, initialize and solve. Now, let's first, before we do any of the upstream, let's first look at the equations, because that's where, then run.gms is, rather than, if we're working on Excel, if we're running on Apple computers, which I don't very often, but if you're running on Apple, it's helpful just to use GAMS as the script for controlling the model. So here I'm going to say GAMS DICE SP. So this is what I would call a piecemeal sensitivity analysis. I'm going to change one thing at a time. And I'm going to say, the first one I'm going to say is the full stochastic model. And then I do 5 models that are deterministic. So this is going back to what Bill was talking about. This is act then learn, or learn then act. So the learn then act approach is we basically define what the scenario is we're going to do. So never 5, 10, 15, 20 are for if we know in advance that there's going to be a catastrophe, or that suddenly the cost is going to go up dramatically in that period, then that's with anticipation. Whereas the stochastic model is where we can't anticipate. Once we've run those runs with the GDX file, then we transfer the results. We merge the results from the GDX files from the output. So this GDX merge pulls together all the GDX files that have been solved up till now and pulls the parameter called a pivot report out and sticks it into a thing called merge.gdx. And then this is, again, a programming trick that I find very helpful with pivot tables. Because one of the great things about pivot tables is you can go in and you can take like a ton of data and you can pivot through to find stuff that's interesting. But the problem is if you pivot to something that's interesting, and if you don't save the model and you pivot to something else that's interesting, you lost the thing that you thought was interesting because you have to pivot back to it. So there's the ability to sort of pivot through and find stuff. So the thing that's useful is to be able to every time you pivot to something that's interesting, save the file with a different name into the same directory. So I'll generate this the common way. So I'll generate a ton of data of output files from a pivot report. I pivot through something that's interesting, and then okay, consumption, that's cool. Save it, call it consume.xls. Pivot again, capital stock. Save capital.xls. Discount, anytime you find something interesting, you save that file. And then this statement here, it says again, it's a little bit of Windows. It says for **f in this set star.xls, do call. So this basically will look for every XLS file in that directory, and when you generate a new set of results, pivot table results, it'll reload the new pivot table in there. So that's just one way. But for our purposes, we don't have to, that's just, again, something more advanced. So let me just jump through the equations. So it's the same as what we've done. Everything is the same. It's a subset of what was in the equations that I gave to you. But there are a couple of changes. So just to highlight, one thing that we do is we have a set called TE. So I had mentioned this on Tuesday, that when you solve integrated assessment models, it's very helpful to distinguish between the economic horizon and the climate horizon. So this is a model that only runs over one horizon for economic activities and a separate horizon for climate. So here we have over TE, we keep track of the capital stock output, we keep track of, this is energy and industrial use of energy, that's abatement cost. These are all economic decisions. So they go over one horizon. And then here we have consumption over all periods is equal to output minus abatement cost minus investment. So notice that this one doesn't go over T, this goes over the full set. And so for the periods that are beyond the economic period, in those periods we fix Y and we fix I. So along that period, over the longer horizon, we let those guys be, we fix those guys, and that way we keep track of damages that take place in the post-terminal period. So you're dogenizing everything through the economic period, and then in the outer horizon, you're keeping track of how, because then that captures the idea that abatement measures you undertake during the economic period have implications on consumption in the post-terminal period. So this captures the transition, the terminal effect through climate then is captured, even though the climate impacts last for a long, long time. Because we run the climate model then 300 years, the economic model we run 75 years. And with DICE, this makes a big difference because then you avoid the economic model, you have discounting going on, so if you go out 300 years, you get prices that are so close to zero that you're creating numerical problems. So here you avoid the numerical problems of doing lots of operations out there, but you keep track of what the damages are off the end of the model. Okay.
What happens to the emissions after the economy?
So the thing is, we're tracking then, in this formulation, we track an approximation of how emissions, we assume that emissions in the post-terminal grow smoothly. So you basically assume that everything, at that point, you're on a smooth path. And that it can introduce an imprecision, but in fact, it works. It's compared to the problems you have with keeping numerical precision when you have high rates of discounting, this turns out to be a much less, anyway. So there's the utility over the state S, and again, that's looking at all time periods for state S, and then this is expected utility, again, with constant relative risk aversion. And then finally, as part of this process, we can terminate the model, the method I described in the last lecture with capital targeting. K term is a parameter which you put in the model to tie down the terminal capital stock, and then we adjust that. So if we look in the solution, so that's the equations for the model. So if I look at the so DICE SP, if I look at solve, so this is a loop to solve the model. So the solution of the model says K iter is the number of iterations we run through the model. We say once we're inside the iterations, we look at the last time period and we set the capital targeting equal to the last period capital times the growth rate, the growth factor in that period. And then all of the rest of the factors that we fix in the post-terminal period, we fix based on how much stuff grows off the end of the model. So gamma of T is a factor that represents potential GDP growth out beyond the economic horizon. And then we solve the model, and then once we've solved the model, we iterate through. We may run more iterations than we need, but because we're using CONOP, the thing solves very, very fast. So just running 15 times doesn't affect it very much. Once we've got this, then we save the basis. The bases directory keeps track of the solutions. So we save the basis. This is the BAU basis. We generate a pivot report saving the values from the BAU. And then we do an iterative loop. In this case, we turn off the BAU, which essentially in the equations, you can see that turns on the damages. And once we have the damages, we rerun the model and do the scenario. So it's looking at one business as usual solution with no damage, and then we do one solution where we optimize between accounting for the effect of catastrophic loss. So finally, let me just So the final thing is in parameters. This is all the same parameters we had before, but the key thing at the bottom here is it's keeping track of, down here is going to set the catastrophic state of the world depending on which scenario is realized. And so this is basically saying, in the equations, there's an equation called if-cat that says if there's catastrophic damages occurring in state S, period T, it says if we're not in the never scenario and state S and T has been realized, then set the if-cat equal to 2. And otherwise, if we're not on never, then it says if we're running a scenario which is with a scenario which is ID, which is a year, then it says the category. This specifies that we apply catastrophic losses after the period of after the ID. So let me see if we can do this. If we say so in the dice damage function, you have a variable that says the damage fraction of output is driven by average temperature changes, and then if there's catastrophic damages, then this is this damage estimate. And here I'm just rotating the damage thing around the origin. So this multiplier, if that's equal to 0, then there's no catastrophic damages. If that guy increases, then the damage curve rotates around about that point. This was the point this is something that Bill was talking about yesterday. He was saying that, recall he was pointing out that when you change the catastrophic damage, he was making the point that it can be misleading to simply change the slope from the origin. So if that's catastrophic. He said that's more common, you think about there being a given level of damage, he suggested that you should change both together so that there's going to be a point where it rotates around. So if there's catastrophic losses, then basically that catastrophic equation, you can simultaneously change the intercept and the slope to get it to go up more rapidly at that point. That was the point that he made the last time. So I thought it would be useful for us just to go off as groups. So the model as it's set up, it's already set up to run for the set of scenarios with stochastic and anticipation. And I thought we could just go off into groups and have different interpretations of what the catastrophic, how you introduce catastrophe into the model. I've done one simple thing where I just did a multiplication effect of the catastrophic thing, but I'd like to think about what that function is and do different versions of it and just see how that affects the results. You can definitely do that, but that's a lot more work than you can do in 1 hour. So the idea would be, in this I was thinking it might be useful, maybe we're running we have until 12:30, right? So I thought this is something we could probably do basically, if that's okay, I don't know. So if you guys form groups, I'll post, I'm gonna right now make sure that the directory is up on my platform, and I'll send you a message. So the assignment as a group is, what I'd like you to do is think about the catastrophic damage and how you have to do a little bit of math to figure out. You could just do a thing, now I've set a value of 2, so you could just change the multiplicative thing and just run the model and compare the stochastic solution versus the other ones, and harvest a couple things out of the results from the pivot table and just put them into a thing and try to interpret what you're getting out of the model. The idea is it's more a matter of just let's go through the process of setting the model up. As I said, 3 persons per group. The least experienced computer programmer should be in charge of the computer, if possible, and just tied together. This is not a matter of right and wrong. It's more just getting everybody to run the model and come together and try to make sense of what comes out. Okay.